So what we'll do in the first hour is continue with the new SM, the standard model extended, or with the dimension 5 non-renormalizable terms. And let's do one more model that I will explain related to neutrino masses. And that's 1 hour. Then we'll do tea break, which is a good part of the day. And then we'll do the second hour. We'll start a little bit of particle cosmology, as much time as I have. Dark matter, baryon asymmetry, we'll see what we can have of these. And we stopped yesterday with the neutrino spectrum and adding dimension 5 terms to the standard model, or these non-normalizable terms. The main effect is that it gives neutrino masses, and very nicely it gives them masses that are on a scale much lighter than of all the other standard model, massive standard model particles. All the standard model particles that have mass, the mass scale is V, and for this now it's V squared over lambda, which by definition is much lighter than V, because lambda by definition is a scale much higher than the electroweak scale. So we have in this framework not only an explanation of the neutrino masses, but also of why they are much lighter than all the other particles, which make this a very plausible explanation or source of neutrino masses. And it implies that they are Majorana neutrinos. But that's a theoretical thing, not yet an experimental. So we can move on. We did the spectrum. The change from before is 3 very light neutrinos. Let's see about their interactions. So again, these LL55 terms involve essentially only the neutrinos and the Higgs, so we'll see about that. Neutrinos do not couple to the gluon. They are singlets of SU3 color. They do not couple to the photon. They have no electromagnetic charge. So there is no effect on the strong or electromagnetic interaction in this extension of the renormalizable standard model. Before there were mass eigenstates, we could see the Z interaction with the neutrinos at any basis, and they were universal. Now we have to move to the neutrino mass basis, neutrino 1, neutrino 2, neutrino 3, and it's easy to see, I don't do it here, that the Z interactions remain universal in the mass basis for the neutrinos. So there is nothing new here, except that now we moved from Ni E, Ni mu, Ni tau to Ni 1, Ni 2, and Ni 3. And what's interesting, I think on the level of principle, but perhaps not practically observable, is the modification for Yukawa interactions. So in the renormalizable standard model, the neutrinos are massless, and they do not couple to the Higgs. They don't have Yukawa interactions with the Higgs, and that's related to their masslessness. Now, these dimension 5 terms, LL55, give us not only neutrino masses, but also Yukawa interactions. There is an interaction, a usual Yukawa thing, or almost usual, a single Higgs field and 2 neutrino fields, and also a coupling. Since these are non-normalizable, you can have this type of thing, 2 Higgs fields and 2 neutrinos. And these interactions are still diagonal and not universal, the same as for the charge fermions, and proportional to the mass, the same as for the charge fermions. The Yukawa couplings here are particularly tiny, so they are proportional to the neutrino mass over V, which is 10 to the minus 12 and smaller. So these are extremely small Yukawa interactions. When I say that it's not of practical implication, it's because of that. We will not observe it. But there are two interesting things here. First, it's not the Majorana nature of the neutrinos is also here. This Yukawa coupling violates total lepton number by 2 units. Okay, it's not psi bar psi. It's neutrino neutrino. Okay, 2 neutrinos. And the second thing is that while these Yukawas are proportional to the mass, as for the charged fermions, the proportionality factor is different. In the charged fermion, it was square root of 2 over V, and here it's 2 over V. Again, has to do with the source that is different, it's dimension 5 terms. If we could have measured the Yukawa couplings, they would not, the 3 neutrinos would lie on a straight line, but it will have a different slope than that of charged fermions because this proportionality factor is different by square root of 2. But we cannot measure, so we can just imagine this plot. Yes?
So that interaction LH, it's not a new bar of T, it's just new.
Again, which interaction?
The new I, right?
Here, yes.
So it's not a bar over that.
Right, it's not a bar.
But then how is it a scalar? Okay. So then how will it be a scalar? That's what
there are, I always forget where the chalk is, and then I do 360 degrees round and find it. So the combinations that can make a Lorentz singlet of 2 fermions are not just L bar right, but also L and right. And this is LL.
It's LL.
Yes.
Okay.
See, if it's possible to have a mass term, not the H here, but M, then it's also possible to have a scalar here. A number, a mass, and a scalar field transform in the same way under Lorentz. So these two combinations are the combinations that enter Majorana masses, and they can also enter a Yukawa coupling because these can be contracted to a singlet of the Lorentz group.
Oh, okay.
Okay. So that was for the Z, no change. For the Yukawa, yes, there is a change. It was 0 in the renormalizable standard model. It's different from 0, has interesting features, and it's unfortunate that we will not see it in experiment because it would have been nice to see another straight line, and that would have proven the Majorana nature or even the source from this dimension 5 terms, but we cannot do it experimentally. Where there is a big difference is in the W-mediated interactions. The charge current mix it, the charge current weak interactions. So in the renormalizable standard model, the W couplings to the leptons were universal. Ni bar E, ni mu bar mu, ni tau bar tau, with the same coefficient G over square root of 2. And this was because there was an interaction basis that was simultaneously the mass basis for charged leptons and for the neutrinos. And that was a result of the fact that neutrinos were massless in the renormalizable standard model, and any rotation of the basis for neutrinos is there a mass basis. Now they are not degenerate, and so similar to the quark sector, there is now no interaction basis that is simultaneously mass basis for charged lepton and mass basis for the neutrinos. The transformation that you take the 3 left-handed lepton doublets, LL1, LL2, LL3, into the mass eigenstates of the charged leptons, E left, mu left, tau left, is accompanied by it's a unitary transformation with VE left from the left. The transformation that takes from the same interaction basis, the transformation of the 3 left-handed lepton doublets to the neutrino mass basis is a different, in general, matrix VD left. Both are unitary matrices. So to go from this in the interaction basis, where this is universal, to the mass basis, you have an insertion of VE left here, an insertion of VE left dagger here, and so this together, VE left dagger puts here a mixing matrix U, which is the analog of the CKM matrix in the quark sector. The same thing now happens also in the leptonic sector, which makes the leptonic charge current weak interactions in this extension of the initial 5 terms of the renormalizable standard model. Now they are neither universal nor diagonal. So that's a big change from the renormalizable standard model related to the fact that the neutrinos are now massive and not degenerate. And so, similar to the quark sector, these diagonalizing matrices depend on the basis from which we started. This combination is invariant to that. It's independent of the choice of the interaction basis. It's always the same. The elements here, so these are the names of, on the left we have charged leptons, the mass eigenstates, E, mu, and tau, so these are the columns. And on the right, there are the neutrino mass eigenstates, 1, 2, and 3. So this is the leptonic mixing matrix, also called sometimes the PMNS matrix. For 1, I think, Bulgarian, Pontecorvo, and 3 Japanese scientists that introduced the idea of oscillations, and the 3 of these suggested the first mixing matrix, but in the context of a different model, actually. So here is the nu SM lepton interactions, electromagnetic, universal, omni magnet charge leptons, neutral current weak, universal, both in the charge lepton and neutrino sector, charge current weak, now similar to the quarks with a unitary matrix for these pairs, and a Yukawa, which is proportional to the mass, so it's diagonal, proportional to the mass, but with a new proportionality factor. Next step, accidental symmetries. They are always a subgroup of the symmetry of the kinetic terms, which is this U3 to the 5th. In the mentioned 4 terms, the renormalizable terms, the Yukawa broke it into U1 to the 4th, U1 baryon number, electron number, U number, tau number. Now with these additional LL55 terms, all the 3 lepton symmetries, E, mu, and tau, and even their sum, the total lepton number, are broken, and this model has left as an accidental symmetry a single U1 baryon number, where the quarks have charge a third and all other fields are neutral. So it breaks what we call lepton, there is here lepton flavor violation. Electron number can change, mu number can change, tau number can change. That's flavor violation, lepton flavor violation, and also lepton number violation. The number of leptons minus antileptons in the initial state and leptons and antileptons in the final state can be different, these numbers. Now, experiments, the neutrino oscillations experiment, established that all 3 flavor symmetries are violated. U1E is not conserved, U1 mu is not conserved, U1 tau, we've seen that in experiment. We did not see yet in experiment violation of total lepton number. The neutrino oscillation experiment conserved lepton number, so we did not see that yet. This model predicts that it is violated, but you need a different kind of experiment, not neutrino oscillations, but the most likely to discover violation of lepton number is neutrinoless double beta decays. parameters. Again, it goes here through this method of counting how many physical parameters there are. In the lepton sector, in the renormalizable standard model, there were only 3 parameters, the charged lepton masses, or the charged lepton Yukawa couplings, ME, MU, and tau, or equivalently YE, YMU, Y tau. And now we have 9 additional parameters, the 3 neutrino masses. In this mixing matrix U, there are 3 mixing angles, 3 real parameters, and different from the CKM matrix, which had 1 imaginary parameter. Here there are 3 imaginary parameters. This is related to the Majorana nature of neutrinos. In the quark sector, you can redefine the phases of the quarks, maintaining the quark masses real and removing phases from the mixing matrix. Here, since the neutrinos are Majorana, redefining their masses introduces phases into their masses. You don't want to do it, and so you cannot redefine the neutrino phases, and that's why you are left with 3 phases. If you are working on this topic, you should do this exercise explicitly to see how it's working. But we have here 3 new sources of CP violation, and actually, not sure whether it's mentioned. Actually, the phases in the leptonic sector, in particular the one that is the analog of the Kobayashi-Maskawa phase, are interesting. So these things can be relevant to a scenario that solves the baryon asymmetry problem by a scenario that is called leptogenesis. I may come back to it in the next hour, but that's why CP violation in this sector is interesting and pursued by experiment to establish whether it's there. But so the newest M, so to remind you, the standard model has 18 parameters, the newest M has 27. And of the 9 new parameters, we've measured 5. The 3 mixing angle in U are all measured, and 2 mass square difference for the neutrino masses are measured. We don't yet know the absolute scale, and we don't yet know the phases. So in the newest M, we still miss 1, 2, 3, 4 parameters. We don't know them yet. It's likely that in the not too far future, we will know 2 more out of these 4. We may know the phase that is the equivalent or the analog of the Kobayashi-Maskawa phase, and we may know what is the absolute scale of neutrinos. We'll see. Yeah, let me just mention here one thing. So in the CKM matrix, it's very close to being a unit matrix. All the off-diagonal terms are small in CKM experimentally, and the diagonal terms are very close to 1. This is not at all the case for the leptonic mixing matrix. Sinus square being 0.3 implies that this entry here is of order 0.58 or something. This S23 implies that square 0.56 means that this is of order 0.7. So the off-diagonal terms, except this which is a little small, are order 1. We don't know a priori these are independent parameters. It has been somewhat surprising to the community that mixing angles in the quark sector of diagonal terms are very small, and here they are order 1. It may be a hint to some mechanism that determines the size of these things, but we are not sure how to interpret this difference between the lepton sector and the quark sector. So we still don't know the Dirac phase. It's a major goal of future experiments, particularly out of Dune. And the Majorana phases, very difficult to see how we will know them. Affects only lepton number violating processes. So they play a role in neutrinoless double beta decay, which is violating lepton number, and we may know something about them if this is observed. So how can we gain further support to the idea that these dimension 5 terms are the source of neutrino masses? The first thing is neutrinoless double beta decay. We would like to see a signal here, to know that lepton number is violated in nature. This will be a very strong support beyond the fact that neutrinos have masses and they are very light, which support this idea. This will give a further strong support. In the contrary, there is also search for lepton flavor violation in various decays of charged leptons, or the Z, or the Higgs. The newest M predicts that all of these go, but at rates that are branching ratio, something like, I don't know, 10 to the minus 50 or so to this, so completely unobservable. So if we observe any of these, it will mean that there are sources of lepton flavor violation that are not included in the newest M. So observing this will exclude the idea that that's it, that explains all that we see. In particular, that the newest M is the only source of the breaking of U1E cross U1 mu cross U1 tau. It cannot explain if any of these happens in a rate that is observable to current experiments. And this goes back to the scales of beyond the standard model. The neutrino masses in this model are v squared over lambda times diagonal entries of this matrix there. So actually the community, which we think that the standard model is effective field theory, we should include this term before discovery of neutrino masses. And since we know that the scale, the cutoff scale of the standard model, the highest possible is the Planck scale, it gives kind of a lower bound on what to expect from neutrino masses, even before we measure them, and that's of the order of 10 to the minus 5 electron volt. So if we search for neutrino masses and will not find them up to 10 to the minus 5 or so electron volt, it should have been surprising to us. We should not have expected that neutrino masses are really zero, because we know that the standard model is a low energy effective theory, also for other reasons, and then this is kind of the minimum where they should have resided. If you think that there is grand unification, so that there is a scale of new physics at around 10 to the 15 or 10 to the 16 GeV, we should have expected their scale to even be higher than this lower limit, around 10 to the minus 2 electron volt. Now we reverse, here is what we may have thought about the scale of new physics and what it implies to neutrinos. Now we know what the neutrino masses are, so let us use that to say something about the scale of new physics. We know that there is at least one neutrino heavier than 0.05 electron volt, the square root of the largest mass square difference, and that puts an upper bound on the scale. It's v squared over mn. We know mn is larger than something, so we know that the scale is smaller than something, and that's 10 to the 15 GeV. So we learned in this framework on a new scale in physics. If the Z couplings are for some reason small, then the scale would be even lower. This is an upper bound. This is if the couplings there, the dimensionless couplings that are relevant are order 1, then the scale is 10 to the 15 GeV. If they are smaller, then it would be even lower. So we learn on a new scale. It's significant that it's below the Planck scale. It's a proof, for me at least, that there is a scale of quantum field theory below the Planck scale where the standard model above which is not longer a valid theory, and it's only a low energy effective theory. That's the strongest proof of that statement. but also it's extremely close to the grand unification scale, and maybe it's not an accident. Almost all grand unified theories predict exactly this, they generate effectively these dimension 5 terms and predict that neutrinos are massive with a mass scale which is v squared over m gat. So maybe it's a supporting hint that there may be grand unification in nature, the proximity of these two scales. So here's a summary of the newest M. I think all particle physics results of terrestrial experiments. Okay, so putting aside cosmology for the moment, are accounted for in this framework. The renormalizable standard model is not because of neutrino masses, but the newest M is. So here was the definition of the model, the same 3 lines as the standard model, but now we added the dimension 5 terms. The Lagrangian was the renormalizable standard model Lagrangian, plus a set of dimension 5 terms involving 2 scalar fields and 2 lepton doublets. And the difference from the standard model in the spectrum was that we now have 3 neutrinos mass eigenstate. They have masses and can be distinguished by their masses. So this is the new entry, and the names here, Ni1, Ni2, Ni3, while before it was Ni, Ni, Ni tau. The interactions, the change is in the charge current weak interactions, where it's no longer universal, but has a unitary matrix for the various pairs of charged leptons and neutrinos. And the Yukawas are also changed. Now also the neutrinos have Yukawa couplings. They are still diagonal, proportional to the masses, different factor of proportionality. The accidental symmetry is smaller than the one. It's a subgroup of the one of the renormalizable standard model. We are left only with baryon number, and we have 9 new parameters, 3 neutrino masses, 3 real mixing angles of the leptonic mixing matrix, and 3 phases, all of these characterizing the W interactions with pairs of charged leptons and neutrinos. So these are the modifications, but now within this framework, all that we've measured in experiment, so not the dark matter problem, not the baryon asymmetry, we do not solve fine-tuning problems, but all the measurements conducted by humanity on Earth have an explanation in this framework. Now, this is a low-energy effective theory. Low-energy effective theory means that there are heavy degrees of freedom. Heavy is here much heavier than the electroweak scale, and they are not playing a dynamical role in the processes that we measure because they are too heavy. And their effects come into expression via the non-normalizable terms of the standard model. And the cutoff scale is roughly the mass scale of these new degrees of freedom. Now, if we have a certain low-energy effective theory, usually there are several possibilities as to the full high-energy theory that includes these heavy degrees of freedom in it that can produce the low energy. So to know which of these sources we have to produce directly, usually the heavy particles. As long as we do not do it, we have several options as to what is really the physics at the high scale. What kind of degrees of freedom are there that gave us the non-normalizable terms whose effect we did measure. So here I now will present the simplest full model. It's called full high energy theory. It's sometimes called UV completion, ultraviolet completion. This means completion at high scale. That gives as an effective low energy theory the newest M. And I also mentioned that this is perhaps the simplest, but not the only framework. And there are at least 2 more that produce the same newest M as the one that I will now describe. So I call that the NSM, and we see why, so I define it, extract the Lagrangian, the spectrum, the interactions, and argue that the low energy limit of that is the new SM. Let me say there is a rigorous mathematical procedure called integrating out. If you have heavy degrees of freedom that are much heavier than the energy scales in which you are interested, then you integrate out these degrees of freedom. It's a procedure by which you are left only with the non-normalizable terms and the effect of the heavy degrees of freedom, but the heavy degrees of freedom do not appear there anymore. So moving from a full high energy theory to an effective low energy theory is a well-defined process. So it's not a question of guessing. So here's the definition. Same gauge group, local symmetry as the standard model, same scalar content, same spontaneous symmetry breaking, and the only difference is in the fermion content, where I now add 3 copies of right-handed fermions that are singlets of SU3 color, singlets of SU2 left, and carry no hypercharge. So they are singlets of the complete standard model gauge group. So that's the modification to the standard model or its extension. So since I did not change the symmetry, all terms that were allowed in the standard model are allowed also here. So all the terms that do not include these new fields are still there. All the fields are in this model. The symmetry is the same. And so I now write a renormalizable model. So part of it is the standard model, renormalizable Lagrangian. And we only have to ask what kind of additional terms that involve these n fields we can add. So first of all, okay, so let me write and then I'll go. So there are Majorana mass terms for the new degrees of freedom. There are Yukawa, and there is, of course, the kinetic terms. So since they are singlets of the gauge group, then the covariant derivative is the same as the space-time derivative. Okay? They do not transform under any of the local symmetry. We don't have to compensate for that by coupling them to the gauge boson. So that's why it's written here d mu rather than, so del mu rather than d mu. Space-time derivative and covariant derivative are the same for these fields because they're singlets of everything. Second, they carry no charge. They do not transform under any of the imposed symmetries. And that's the situation where the Majorana mass terms are allowed. So every allowed term we should write. And so this is the Majorana mass matrix for this. It's a 3 by 3 complex matrix of mass terms. And for Majorana masses, such matrices are always symmetric because it's not psi left bar, psi right, it's the same field. So, yeah, symmetric. While the Yukawa, that are now possible, left-handed lepton doublets and this thing, and the quantum numbers here are of phi dagger, general 3 by 3 complex of dimensionless coupling. So these are the additional terms, kinetic, Majorana mass terms, and Yukawas, which were not there before. So what is the spectrum? So now we have a 6 by 6 neutrino mass matrix, a mass matrix for all the fields that are singlets Q of SU3 color and carry no electromagnetic charge. Right? All of these fields, fermions, that do not transform under the exact SU3 cross U1 symmetry. There are 6 such degrees of freedom. The 3 knee left, the upper component of the left-handed lepton doublets of the standard model. And now we have also the 3 N right. All of them are singlets of SU3 color, no electromagnetic charge, and there are 6 such degrees of freedom. There is a 3 by 3 matrix for NRI, NRJ, and there is the Dirac mass matrix coming from the Yukawas when replacing the phi field with its vacuum expectation value. This is this MD. This MD is the mass matrix coming from the spontaneous symmetry breaking and the Yukawa. So there are 6 neutrino mass eigenstates. This has to do with their Majorana nature. For the charged fermions, all of them are Dirac fermions because they are charged. So by definition, they cannot be Majorana particles. And 3 Dirac mass eigenstates have 12 degrees of freedom. For the neutrinos, we also have 12 degrees of freedom, but the Majorana has 2 degrees of freedom. So there are 6 of these, 3 of these, but it's the same number of degrees of freedom in each sector now. So what does this matrix imply?
You see, there is a question online.
Yes.
So the question is from Debabrata Sahu. Do we need to add 3 copies of NR or we add less? We can add less.
Yeah, so we need at least 2. Okay, so if we have 1, okay, I did not, we would have, we want to explain the light neutrino masses. If we had 1, then 1 of the light neutrinos would get mass and 2 will remain massless. If we have 2, then 2 light neutrinos would get masses and 1 would remain, would get masses and 1 would remain massless. This is a possibility, so this gives a prediction that the light neutrino masses are hierarchical, that the lightest is massless. And we know then the masses of the other are the square root of delta n squared because one thing there is massless. So this model has prediction. With 3 or more, all 3 light neutrinos get masses. So in a sense, 3 is the most general thing for the low energy phenomenology. A larger number would not make a difference. A larger number of this, what would be heavy neutrinos, in a minute we'll see that. So we could have 2. That's a model with further predictions about the neutrino spectrum. 3 is the most general possibility to give all of them masses, all the light neutrino masses. So let's look for simplicity first. If there were only 1 generation of a lepton doublet and a single L left and a single N right, then the mass matrix would be like that, 2 by 2, MD left diagonal, MN here. And the mass eigenstates, you need to transform this into a diagonal matrix. And the thing here is that we will assume, that's not part of the model, but that's what of interest to us, that this mass scale, that we don't know a priori what it is much larger than the electroweak scale. So this is a parameter of the theory, a dimension full. In the renormalizable standard model, we had 1 dimension full parameter. Here we have more, all the entries in the MN matrix. With 1 generation, it's 1 new dimension full parameter. And for the sake of good phenomenology, we assume that it's much larger than V. In this case, to leading order in V over Mn, we have 1 heavy state with mass that is at leading order Mn, and 1 light state with a mass that is Md squared over Mn. And a simple way to see that this is the case is that when you diagonalize such a matrix, the determinant and the trace are not changed. So the trace is Mn, and to leading order, these 2 masses are, this is very small, so to leading order, it's Mn. And the determinant is Md squared of this matrix. And the determinant of the diagonal mass matrix, Md squared over Mn times Mn, is Md squared. So these are the 2 eigenvalues to leading order each in V over Mn. And the diagonalizing matrix, cosine theta, sinus theta, minus sinus theta, cosine theta, this rotation angle is also small. It's md over mn, once we assume this hierarchy. And so, in this model, we have really three scales. The scale of the light neutrino, the electroweak scale, and Mn. By assumption, this is much larger than that, and by the same assumption, this is much lighter than this scale. And moreover, the larger Mn, the smaller the mass of the light neutrino. And so this is the reason that this model is called the seesaw mechanism. You have two neutrinos sitting on a seesaw, the heavier one of them, the other one, well, it goes reverse seesaw. The other one becomes lighter. Moreover, this mixing angle is the transformation for the basis where you have a neutrino that came from a doublet and a neutrino that came from a singlet of SU2. And if the mixing angle is small, it means that the light state is almost purely coming from the doublet, and the heavy state is almost purely coming from the singlet, up to deviations that are of order md over mn. So this is the component of the doublet in the heavy state, and it's the component roughly of the singlet in the light state. I hope I don't confuse you too much. So that's with one generation, and the extension to three generation is kind of straightforward. It's a bit more complicated, but this is the spectrum of this model under the assumption that all, if you want, the eigenvalues of the heavy, of the Mn matrix are all much heavier than the scale, the electroweak breaking scale. So there are three heavy Majorana neutrinos. We call them N1, N2, N3, of masses M1, M2, and 3. They are very close to being with well-defined transformation property under SU2, to being the singlets, but they have a small component of a doublet. There are three light Majorana neutrinos, Ni1, Ni2, Ni3, masses M1, M2, M3, of order V squared over Mn, and they are approximately doublets, but have a small component of a singlet. And so the model has three mass scales. Unlike the renormalizable standard model, it has one, V. Here there are, so in the standard model, all massive particles, their masses are of order V. Here there are the scale Mn, where there are singlet fermions, singlet neutrinos, singlet of SU3 color cross U1 electromagnetism, all charge fermions, and the W, and the Z, and the Higgs have a mass of order V, and there are three very light neutrinos with mass of order V squared over Mn. Okay. Interactions. So that's the spectrum. Okay. Three very heavy neutrinos, three very light neutrinos, and all the charge fermions and massive bosons in between. The neutrinos, both the heavy and the light, carry no SU3 color, so they don't couple to the gluon, no electromagnetic charge, so they're not coupled to the photon, and there is no anything new about the strong and electromagnetic interactions, while all the others are modified. So the charge current, this is okay, a bit advanced, but we have still three charged lepton mass eigenstates, E, mu, and tau. The thing that transform as a singlet of SU3 color and charge -1 under U1 electromagnetism. There are three such states still. But there are 6 states which are singlets of SU3 color and neutral under U1 electromagnetism. And so the W interactions connect between these 3 charged mass eigenstates and the 6 neutral mass eigenstates. If there was not the small component of a doublet in the heavy neutrinos, we would not have this thing here that connects the charged leptons to the heavy states. But these are the mass eigenstates, and they do have a small component of a doublet to which the W does couple. So the W couples to the small component of a doublet within this heavy mass eigenstate. But the thing here is that the mixing matrices are between mass eigenstates, and so we have 3 charged lepton, 6 neutrinos, and the mixing matrix is 3 by 6. And yeah, this is the notation. And in this part, okay, 3 by 6, in this part of the matrix, 3 by 3, all entries are very small. They're just of the size V over Mn, which tells us the size of how much a thing coming from a doublet is in the heavy mass eigenstate. And since these are very heavy, we will not be able to measure this part in experiment, in these models. But similar to the NUSM, the charge-Kern-Wick interactions are neither universal nor diagonal. There is a mixing matrix. Also in the coupling of the charged leptons to the light neutrinos. I will not go into the Z interactions, even though they demonstrate something that I said, so maybe I just mentioned that. So I said that it's a special feature of the standard model that the Z interaction are universal. Unlike the photon and the gluon, which correspond to exact gauge symmetries and therefore must be universal, the Z I said had to do with a special feature that in the standard model, the renormalizable standard model, all states of a given SU3 cos U1, SU3 color cos U1 electromagnetism transformation come from the same SU2 cos U1 representation. If that's not the case, then the Z couplings will not be universal. This model is an example of a model where this feature of the standard model does not hold. Not all the particles with the same SU3 color cos U1 electromagnetism quantum numbers, or specifically those that are singlets of SU3 color and neutral under U1 electromagnetism, they come from 2 different SU2 cos U1 representation. 3 of them, these light things, come from doublets of SU2 with hypercharge -1/2, and 3 of them, the ends, come from singlets of SU2, singlets of U1 hypercharge. And in this case, the Z has off-diagonal couplings, and its couplings are not universal. The effects are small. They are of this order, the deviation from universality in the Z coupling to the light neutrinos, but they are there in principle. And it demonstrates that the standard model has this unique feature that it may be lost when we extend it. Okay, I will not go into details about the Higgs-Yukawa. It's now, as for the first time, we see off-diagonal Yukawa couplings in this model. And I said also that this diagonality of the Higgs coupling is again related to unique features of the standard model, and these unique features are violated here, but I will not, too complicated for now. So just a word about the heavy states. We will not produce them probably in experiment. Their mass scale is likely to be at the 10 to the 15 GeV or so. So we will not be able to probe their properties in experiment, even though it would have been very interesting if this model is indeed realized in nature. But there is one implication that is very interesting. So the Ni particles, these heavy mass eigenstates, they are not stable. There is no symmetry that protects them from decay. And they decay to a light lepton, either a neutrino or a charged lepton. and a boson. And the boson is either the Higgs, which now has off-diagonal couplings, including to the heavy and light, the Z, which also couples to heavy and light, and the W, we saw before the 3 by 6, it means that it also connects this right part of the matrix, connects the heavy mass eigenstates to the charged leptons via their coupling to W. So it can have decays either to a neutrino and a Z, or to a neutrino and Higgs, or to a charged lepton and a W. These are the decay modes. And so as I said, by assumption they are very heavy, cannot be directly probed. But these decays turn out could account for the baryon asymmetry of the universe. There are here new CP violating phases in Yukawa and in other parts in the mixing matrix. And actually, since this model is a full model that explains neutrino masses, it was invented for that purpose. And then for free, you get a very nice possible explanation of how the baryon asymmetry was generated. Then this is a very popular idea now, a very shared by a large part of the community, that it's plausible that actually this is the way that the baryon asymmetry is generated. This is called leptogenesis. So it means that first you create an asymmetry in the universe between the number of leptons and anti-leptons, and then there is a standard model mechanism that perhaps in the next hour I'll mention, that converts part of this lepton asymmetry into baryon asymmetry. One can do detailed calculations of how this happened depending on the parameters of this model, and you don't need any particularly large number or small numbers. Numbers of order 1 of the new parameters are very nicely can account for the size of the observed baryon asymmetry. Okay, so these N fields are very heavy. I said that there is a well-defined procedure of integrating them out and getting a low-energy effective theory. If you look in the slides, there is here a pictorial explanation of how the dimension 5 of the effective theory come from renormalizable terms in this full theory. I will not go into that. I'll just say that if you integrate out the degrees of freedom of the 3 heavy neutrinos, you get the standard model as an effective field theory. You get at dimension 5 the terms of the newest M, LL55, and you get also dimension 6 and higher that involve leptons, but they are at present not relevant to phenomenology. So this could be a high energy theory that produces the dimension 5 terms that we have essentially, I think, measured in our experiment. But it's not the only possible high energy theory that produces the newest M at 3 level. This is, I mean, if not at 3 level, there are even more. So this is called type 1 CISO, this NSM model. It's adding to the standard models list of fermions, fields that are singlets of the gauge group. That's what we've done now. Type 3 CISO is also adding fermion fields, but they are singlets of SU3 color, triplets of SU2 left, 0 hypercharge, so it's different representation from that. But at low energy, the dimension 5 terms are the same. And an even more perhaps surprising source, you can add no fermions, add just scalar fields that are singlets of SU3 color, triplets of SU2 left, hypercharge -1. Again, give them a mass scale that is very high, this mu squared, this dagger times itself, this mu squared you put at a high scale, you integrate them out, and you get the same dimension 5 terms. So that's called type 2 CISO. So there are at least 3 frameworks that give the same dimension 5 terms, which says that as long as we did not have a direct access to the heavy fields, we cannot know. So neutrino masses don't tell us if the theory of nature is this, or that, or that, or perhaps something that creates it at loop level and not a tree. To the best of our understanding, it does tell us that we've seen the dimension 5 terms of the non-normalizable standard model, of the standard model as an effective field theory. Open questions. So first of all, this new NSM is a very plausible extension of the standard model. Experiments established that neutrino have masses and mix as predicted by the new SM. They determined 5 of the parameters out of the extra 9. Yet to be answered by experiment is whether the neutrino spectrum is hierarchical or quasi-degenerate. So these are the 360 degrees, and here is the chalk. So it's this. So this is the mass of the neutrinos. And it could be, here is 0. It could be that one of them is massless, and yeah, and the other one, for example, is here, and the third one is here. That is called hierarchical. It could be that they are well above here, somewhere. Yeah, so this is at least, so in this case, this is 0.009 roughly EV. And this is 0.05 EV. And that's hierarchical, okay? It could be that they are all much heavier because all we know is the mass square difference. So it could be that they are somewhere here, in which case they are really very close to each other, okay? If they are heavy but have the same mass square difference, they must be almost degenerate. Okay? Do the calculations and see. So we don't know if it's this case or this. This is hierarchical, and this is quasi-degenerate, and it could be anywhere. This, what we know is that this is not heavier than the EV scale, okay? 20 times larger than that, roughly. So that's the first question. The second is the neutrino mass ordering normal or inverted. So this is what's called normal. Inverted, I put these two here and the massless one here. Or here I put the smaller mass splitting above and this one below. And again, going from here to here over the whole range is a possibility. So we don't know. I don't exactly know why this is called normal and this is considered abnormal, but that's, you know, I think I know actually. This would be very surprising because this means that there is degeneracy in nature. So that the mass, at least 2 or maybe all 3 are very close to each other without a basic explanation. This would be a surprise. We do not see really degeneracy in the charge fermions. So we expect it to be hierarchical perhaps, but that's a naive theorist expectation. We do not yet know whether CP is violated by the lepton mixing matrix. It's hard to believe that it's not, okay? CP is violated in nature. It has the freedom of having it in the leptonic mixing matrix. There is no reason whatsoever that it will not be there. There is no symmetry that can forbid that. But again, we want to see it experimentally. So we want to know if the neutrinos are Dirac or Majorana fermions experimentally. We want to know if there are additional light neutral fermions. These are called sterile fermions. The newest M says no. Only the known neutrinos are light. And We want to know if dimension 6 terms are also important for lepton flavor violation or lepton number violation. So far, we've seen only the effect of dimension 5. I believe that the newest M is realized in nature, but we would like to know what is the full model, what are the new degrees of freedom that generate it. And all of this is part of a rich and exciting experimental neutrino physics program that is going around the world, and some people here are involved. And as I said, neutrinos have surprised us so far many times, even by their very existence. That was first understood because it seemed that there are processes that do not conserve energy, which was a complete surprise. And at that time, early 30s, suggesting new particles that have not been observed or giving up on energy conservation were thought to be equivalent or similarly revolutionary. Nowadays, theorists invent new particles as they wish, as many do. They go crazy with it, and no one would think that energy conservation should be given up. But in the early 30s, it was a very daring thing by a theorist, in this case Pauli, to suggest that instead of violating energy conservation, there are particles that the detectors cannot get. Actually, I don't know if you know, it's a very famous story because he suggested it in a letter to conference participants. He apologized that he could not participate in the conference because he is invited to a party. I don't think that nowadays any serious physicist would dare to say that they are giving up on a conference because they go to a party. I'm not sure that there are many physicists that would prefer a party over a conference, but that's the case. And then he also kind of apologized for suggesting this crazy idea that there are particles in nature that we cannot see. And actually, he thought that we will never see them. So, which in I think 2 decades, the neutrinos were observed and proved to exist. So that was their first appearance on physics, on particle physics, and since then they have masses, they make strange things to the sun, in the atmosphere, etc. So I think that's it for the neutrinos. Yeah, it's time to stop. So, thank you.
Questions?
So why these quasi-degenerate levels lie higher than the hierarchical levels?
Yeah. Suppose you have a mass square difference, m2 squared minus m1 squared. You measure it, and now you can write it, if you want, as m2 plus m1 times m2 minus m1. And so, in a sense, the heavier they are, the more they generate for a fixed delta m squared. The degeneracy is stronger for a fixed delta m squared. The heavier, if you want, their average. This is high, this is twice their average mass. It goes up, they become closer and closer to keep the same delta m squared. So that's the reason. Yes.
So, can you go to the baryogenesis slide? Go back to it. Yeah. Yes, this one. So, these new particles can decay into light leptons, right? As we saw from the interaction term.
They can decay?
Decay into these light leptons, neutrinos and
Yes.
the charged leptons, but they can also decay into the antiparticles, right?
Right.
So, like, is it because of the CP violation that is the reason for the baryon asymmetry?
Okay. I think I understand the question. So you will deduce from the answer whether I do. So the decay, let's say, to a neutrino plus something or to anti-neutrino plus something, that's a result of their Majorana nature. They do not, the mass eigenstate do not have a well-defined lepton number. They are, in a sense, the mass eigenstates are a mixture, what you call neutrino or antineutrino. So that's a result of that. If their decay to a neutrino plus a boson and to anti-neutrino plus a boson, it's the same boson, the Higgs or the Z, occur at different rates, that's the CP violation. Not the fact that it can decay to both, that's Majorana, that's lepton, that's exactly the manifestation of lepton number violation. It comes from their Majorana nature, but a difference in rate, that's CP violation. Since the Yukawas are complex in general, the Yukawas of these heavy neutrinos in the light, then there are many phases in their Yukawa couplings, and that's why there can be CP violation, and it's calculable, okay? And if I get to baryogenesis in the next hour, we may even see the formula for that and understand roughly how it arises.
So this different rate of decay into particles and antiparticles will give rise to the asymmetry.
Yes, yes. There will be preference for producing, let's say, neutrinos over anti-neutrinos in the universe, yes.
So, the baryon asymmetry. So the operator dimension 5. I can generate the baryon asymmetry in dimension 5 or dimension.
Sorry, but I did not understand the question.
So
And
the
slowly
effective
for me.
field operator dimension 5.
And-
I can
and-
generate baryon asymmetry
No,
in dimension
so-
5.
So the baryon asymmetry, to understand it in this scenario, you need to include your heavy degrees of freedom n in the model. The effective dimension 5 by themselves cannot account for the baryon asymmetry. It comes from the decays of this n. So you have to have the scenario of creating the baryon asymmetry this way. The model must include the particles that decay, which are these heavy ones. In the dimension 5 terms, you don't have them. So there you would not, by this you will not see that leptogenesis can happen. You need the full high energy model.
There is an online question. Debabrata Sahu is asking, what is the present status of neutrinoless double beta decay?
Upper bounds,
He just asked this, yeah.
yeah, I didn't explain exactly what they measure. They measure something called MEE. This is a combination of neutrino parameters. It's M1 UE1 squared plus M2 UE2 squared plus M3 UE3 squared. And it's not absolute value of UE1. So that's, you see also how Majorana phases play a role. And M1, M2, M3 are Majorana masses, so this has in it lepton number violation. And they put an upper bound on this, which I don't remember exactly what it is. It's below EV, but still well above 0.05 electron volt. I don't think they can get to 0.05 electron volt. And so I know that it's in between because if neutrinos are hierarchical, then the experiments don't have enough sensitivity. So these are small numbers, M1, M2, M3 in this sense. And then it seems that the experiments, the current technology cannot get to such small values. If they are in such a region, so M1, M2, and M3 are larger, so if they are quasi-degenerate, if they are well above 0.05 electron volt, then very likely at some point the experiments will see the effect. I have to perhaps mention that seeing the effect or seeing the process of neutrinoless double beta decay would be unambiguous signal of lepton number violation, and except for some caveats, a proof that the neutrinos are Majorana particles. But the translation of what is measured by this experiment, so the rate of the process that they will extract into this parameter, has uncertainty. So we will know that it's there, but the exact value has some nuclear matrix elements in it, which we do not have a precise knowledge of it. So qualitatively, it will be revolutionary to see it. Quantitatively, there will be large uncertainty in the translation into this parameter of the newest M. Yes.
So these heavy neutrinos, how heavy are they? I mean, do we
How-
have
heavy?
idea of the masses? I mean,
Okay, so that's so the light neutrinos are of the order of, say, some Yukawa squared, B squared over the heavy mass. What we know is that this combination is, let's say, of order 0.05 electron volt, order of. If this is of order 1, then Mn is of order 10 to the 15 GeV, right? We know what V is, so if it's above 1, then the theory is perhaps non-perturbative. We want a perturbative theory, so that's why this is an upper bound. It could be that Yn is smaller than 1, and then Mn will be something like 10 to the 15 GeV times Yn squared. So the smaller Yn, the lower the mass scale of these particles. We don't know what Yn is, so that's why this is an upper bound. Assuming that Yn is not crazily small, at least for one of, let's say, third generation, I don't know, let's say perhaps at least 10 to the minus 2, then the scale would be at least 10 to the 11 GeV. Still far above the electroweak scale.
and if they're decaying to say Higgs, decay to Higgs boson.
They can decay. One of their decay modes of the heavy ones would be
Yes.
to Higgs and neutrino.
And is it through some loop, leptonic loop?
No, it's through,
Simple.
yeah, so
Okay. Okay.
yeah, so these are the Yukawa. The Yukawas are
Okay.
essentially Yn, but since we want the mass eigenstates, then it's multiplied by this unitary matrix that takes you from the neutrino mass eigenstates to from the interaction eigenstates to the mass eigenstates. But the Yukawa is this Yukawa more or less in the Lagrangian. So it's this.
Okay.
Yeah.
And then can we, essentially the Higgs mechanism and the mass generation, can we relate to it in some sense?
So the Higgs is responsible, the Higgs mechanism
Yeah.
is responsible to this MD up there.
Okay.
This is the Yukawa times the vacuum expectation value, these entries here.
Okay. Okay.
For charge fermions, there is no Mn, and then Md is the Dirac mass matrix, etc. Here, because there is also this ingredient that the singlet things have a Majorana mass, then this is not the mass, but the eigenvalue is Md squared over Mn. Okay, but the Higgs mechanism is here. These are Majorana mass terms
Okay.
that are allowed already in the Lagrangian because the N fields are singlets of the imposed symmetry group, SU3 cross SU2 cross U1. So you have these terms in the Lagrangian. This comes from the Higgs mechanism. These have nothing to do with the Higgs. It's what we call L psi. This comes from L Yukawa. This comes from
So
L psi.
Majorana nature is basically preserves the symmetry SU2 cross U1. It doesn't spontaneously breaks. Can I say this?
Right. These Majorana masses do not break any symmetry.
Yeah, don't
It's
break
only
any
allowed because these are complete singlets of SU3 cross SU2 cross U1.
Okay.
Yes.
Okay.